welcome back to my class in linear algebra. For today, we will take up inverse matrix or the inverse of a matrix. And today I will demonstrate one way of obtaining the inverse of a matrix. First, we define inverse of matrix. Let A be a square matrix, then B is called the inverse of A, written A to the power minus 1 if the product AB, which is equal to the product of A times A to the negative 1, equals the identity matrix I. In the definition, the matrix should be a square matrix. That is, the number of rows and the number of columns of the matrix are equal. This implies that only square matrices have inverse matrices. A matrix that is not a square matrix has no inverse. That is, we cannot find the inverse of a matrix that is not a square matrix. And the condition for the matrix B to be an inverse of matrix A is that the product of A and B is equal to the identity matrix I. If matrix A is a 10 by 10 matrix, then the identity matrix I is also 10 by 10 matrix. Also, the inverse, if B is the inverse of A, the size or shape of matrix B is the same as the size or shape of matrix A. And the inverse matrix B of A is also denoted by A to the power negative 1. And we know from our previous lesson that an identity matrix is a square matrix whose diagonal entries are 1 and the rest of the entries are 0. As I said earlier, today I will demonstrate one way of obtaining the inverse of a matrix, and that is by use of elementary row operations. And there are actually 4 elementary row operations. These are the 4 types of elementary row operations. In the first type, the ith row, denoted by r sub I, and the jth row of a matrix, denoted by r sub j, are interchanged. In the first elementary operations, two rows are interchanged, denoted by r sub I and r sub j. In the second elementary operation, the ith row is replaced by scalar multiple of the entries of the ith row, where the scalar is denoted by k. In the third elementary operation, the ith row is replaced with the sum of the entries of the ith row and the scalar multiple of the entries of the jth row. The scalar multiple of the ith row is obtained by multiplying all the entries of the ith row by the scalar k. Also, the scalar multiple of the jth row, the entries of the scalar multiple of the jth row are obtained by multiplying the entries of the jth row by the scalar k. And the last type of elementary operation, the ith row, the entries of the ith row are replaced with the sum of the scalar multiple of the ith row, where the scalar is denoted by k sub 1, and the scalar multiple of the entries of the jth row, where the second scalar is denoted by k sub 2. And in obtaining the inverse of a matrix, we may use one or more or all of these elementary operations to get the inverse of a matrix, of a square matrix A. And how do we get the inverse of a square matrix using elementary operations? We follow the following basic steps. To get the inverse of a square matrix A, we write initially a matrix of this form. The matrix A and the identity matrix I. The given matrix A is a square matrix and the identity matrix is a square matrix whose size is the same as the size of the given matrix A. And their entries are separated by this vertical line. And using the elementary operations, one or more of these elementary operations, we transform this matrix into a matrix of this form. The first matrix now is the identity matrix, followed by a square matrix, and the second square matrix is now the inverse of matrix A, denoted by A to the minus 1. And to check if the obtained inverse matrix is correct, we simply multiply the given matrix A by the inverse matrix obtained, and the product should be the identity matrix I. Now, this second matrix is said to be equivalent to the first matrix. And we say that a matrix is equivalent to an original matrix if the new matrix is obtained from the original matrix using one or more of the elementary operations. Again, a matrix is said to be equivalent to an original matrix if the new matrix is obtained from the original matrix by one or more of the elementary row operations. Now, we will have an example of how to get the inverse of a square matrix, and we start with a square matrix of size 2 by 2, and we will find the inverse of this 2 by 2 square matrix using elementary operations. For our first example, we find the inverse of matrix N It's a 2 by 2 matrix with entries in the first row 3, negative 2, and entries in the second row 5, positive 4. The first step is we write the matrix of this form. We write the matrix of the form Ni, where N is the given square matrix of size 2 by 2, and I is the identity matrix of size 2 by 2 also, where the diagonal entries are 1 and the rest of the entries are 0. We start from here, from this matrix. It's the given matrix N and the identity matrix of size 2 by 2. The diagonal entries are 1. The diagonal entries are those entries in the same row number and same column number. This is the entry in the first row and first column, and this is the entry in the second row, second column. And the rest of the entries in the identity matrix are 0. And our objective is to transform this matrix into a matrix of the form I, identity matrix of size 2 by 2, and the inverse of matrix N denoted by N to the minus N. We make this the matrix N, and we transform this into an identity matrix. But whatever we do in a row of matrix N, we do also to the same row of the identity matrix I. And if we want to transform this into identity matrix of size 2 by 2, this entry 3 must be changed to 1. And to change 3 to 1, we make use of the second elementary row operation. That is, we replace we replace the entries of the first row. 3 is the number to be changed to 1, and 3 belongs to row 1. Therefore, we replace all the entries of row 1 using the second elementary row operation. And we can make 3, we can change 3 into 1 by dividing 3 by 3, or multiplying 3 by 1/3. But we operate on a row, so we multiply all the entries of row 1 by 1/3, or we divide all the entries of row 1 by 3. This is the second elementary operation, where the first row is replaced by the scalar multiple of the entries of the first row. So to get the new entries of the first row of the equivalent matrix, a matrix equivalent to this original matrix, we multiply each entry of the first row by 1/3, or you can divide each entry of the first row by 3. Divided by 3 is 1. Negative 2 divided by 3 is negative 2/3. One divided by 3 is 1/3. And 0 divided by 3 is 0. The entries of the second row are the same, 5, 4, 0, 1. Now we have changed the original entry 3 into 1 by using this second elementary row operation. Now, the next entry, we start with the first column. If we are to change this into an identity matrix, the first entry is 1, which we have already done. And in the first column, the second entry in the second row must be 0. Now, this 5 must be changed to 0. And if we change 5 to 0, all the entries of row 2 must be changed. This new matrix, by the way, is an equivalent matrix to the original matrix. This matrix is equivalent to this matrix because this new matrix was obtained from the original matrix using the second type of elementary row operation. And if we change 5 to 0, we would get another matrix equivalent to this matrix. And as I said, we change 5 to 0, but if we change 5 to 0, we have to replace all the entries of row 2. And we replace the entries of row 2 with reference to row 1, where we have 1 in the first column. Now, we replace the entries of row 2 by taking the negative of this entry to be changed to 0. Always take the negative of the number to be changed to 0. So 5 would be negative 5. And multiply negative 5 by row 1 where we have 1. And you add row 2 whose entries are to be changed. And this is the this is the third type of elementary row operation, where the second row is replaced with the sum of the entries of the original entries of the second row and the scalar multiple of the first row. Again, the number to be changed here is 5 and it is to be changed to 0. If you want to change 5 to 0, we have to replace all the entries of row 2. So, we construct an operation, we make an operation, we operate on the entries of row 2. And how do we change 5 to 0? Take the negative of the number to be changed to 0. And the number to be changed to 0 is 5, positive 5. Take its negative, you get minus 5. If this is negative 5 and negative 5 is to be changed to 0, take its negative. Negative of negative 5 would be positive 5. So if this is negative 5, you should have here positive 5. If this is negative 5 and negative 5 is to be changed to 0, you take its negative and you will get positive 5 here. Multiplied by row 1. We multiply by row 1 because we started with the first column and we have 1 in the first row. And then simply add the original entries of the row whose entries are to be changed. So we perform this operation. R2 is replaced by negative 5 multiplied by the entries of row 1. The entries of row 1 are 1, negative 2/3, 1/3, 0. Plus the entries of row 2, 5, 4, 0, 1. And perform the indicated operation. Operation indicated here is multiplication. Multiply each of these entries by negative 5. Negative 5 multiplied by 1 is negative 5. Negative 5 multiplied by negative 2/3 is positive 10/3. Negative 5 multiplied by 1/3 is negative 5/3. And negative 5 multiplied by 0 is 0. And to these entries, we add the entries 5, 4, 0, 1. We add negative 5 plus 5 is 0. We have 10/3 plus 4. Now, for us to have a common denominator of 3, multiply 4 by 3/3. Multiply 4 by 3/3, you get 12/3. And to 12/3, you add 10/3. 12 plus 10 is 22/3. And negative 5/3 plus 0 is negative 5/3. And the last entry, 0 plus 1 is 1. And these are the new entries of row 2 in the equivalent matrix that we will now write. Entries of the first row are the same because it is the entries of row 2 that we change. So the entries of the first row are the same, 1, negative 2/3, 1/3, 0. And we now write the new entries of row 2, 0, 22/3, negative 5/3, and 1. We are now done with the first column. We are converting this matrix into identity matrix of size 2 by 2 into this identity matrix where the entries in the first column are 1 and 0, and we have 1 and 0 in the first column. Now we will change the entries of the second column, and we start by getting 1 in the second row, second column. And so we want to make this entry 22/3. We want to change this into 1. And if we change this into 1, this belongs to row 2. We have to change all the entries of row 2. And we make use of an elementary operation. To change 22/3 into 1, we simply multiply 22/3 by its reciprocal. Because we know from arithmetic or from algebra that the product of a number and its reciprocal is 1. So if we want to make this, if we want to change this into 1, we simply multiply 22/3 by its reciprocal, which is 3/22. And 3/22 we multiply by the entries of row 2. Again, this is an example of the second type of elementary row operation. So to change this into 1, we multiply all the entries of row 2 by 3/22. And the entries of the first row are the same. We now multiply row 2 by 3/22. 0 times 3/22 is 0. 22/3 multiplied by 3/22 is 1 because the product of a number and its reciprocal is 1. And negative 5 over 3 multiplied by 3 over 22. 3 will cancel out. And you get negative 5 over 22. And 1 multiplied by 3 over 22 is 3 over 22. So we have changed 22 over 3 to 1. And we are still working on the second column. In the second column now, this entry must be 0. Or this entry, negative 2 over 3, must be changed to 0. And we will make use of an elementary row operation of this form. This matrix is said to be equivalent to this matrix because this matrix was obtained from this matrix by using this elementary row operation. And this matrix is equivalent to this matrix because this matrix was obtained using the second type of elementary row operation. Also, this matrix is equivalent to the original matrix because this last matrix was obtained from the original matrix by a sequence of elementary row operations 1, 2, 3. Now we will change negative 2/3 to 0 using an elementary row operation of this form. The number to be changed to 0 is negative 2 over 3. And negative 2 over 3 belongs to the first row. That means if we have to change negative 2 over 3 to 0, we have to replace or change all the entries of row 1 by using an elementary row operation. And when changing a number to 0, we always take the negative of the number to be changed to 0. The number to be changed to 0 is negative 2/3, and we take its negative, or we multiply negative 2/3 by negative, and you get positive 2/3. And we multiply positive 2/3 by row 2, where we have 1 in the second column. And to the scalar multiple of row 2, where the scalar is 2/3, we add row 1. We perform this elementary operation of the third kind, and we should get 0 in this entry in the second row and second column. We multiply row 2 by 2/3. Row 2, 0, 1, negative 5 over 22, and 3 over 22. And to this product, we add the entries of row 1. 1, negative 2/3, 1/3. And 0. We multiply each entry of row 2 by 2/3. 2/3 multiplied by 0 is 0. 2/3 multiplied by 1 is 2/3. 2/3 multiplied by negative 5 over 22. Before you multiply, you cancel out what can be cancelled or simplify the fractions. 2 over 22 can be simplified to 1 over 11. And multiply by negative 5 over 3. That's negative 5 over 33. over 3 multiplied by 3 over 22. 3 and 3 will cancel out. And 2 over 22 simplifies to 1 over 11. And these are the new entries of row 1. And the matrix equivalent to this matrix is the matrix with entries of the first row given by 0, 2/3, negative 5 over 33, and 1 over 11. We made the mistake here. 2/3 multiplied by 1 is 2/3. And these are the products of 2/3 multiplied by these entries of row 2. And to this product, we still have to add these entries of row 1. Now we add 0 plus 1 is 1. 2/3 plus negative 2/3 is 0. We have negative 5 over 33 plus 1/3. Now for us to have a common denominator of 33, we multiply 1 over 3 by 11 over 11. So that we will have a common denominator of 33. Multiply 1 by 11, and 11 minus 5 is 6. Common denominator is 33, 6 over 33, and change that to lowest terms. You get 2 over 11. And the last entry of the new entries in the first row is 1 over 11 plus 0 is 1 over 11. And these are the new entries of row 1. Now we write the matrix equivalent to this matrix obtained by performing this elementary operation. The new entries of row 1 are 1, 0, 2 over 11, 1 over 11. And the entries of the second row are the same, 0, 1, negative 5 over 22. Now you can see that this last matrix is of this form, identity matrix and the inverse of n. So the inverse of the given matrix n, denoted by n to the power minus 1, is the square matrix with these entries. The inverse of matrix n, entries in the first row, 2 over 11, 1 over 11. Entries in the second row, negative 5 over 22, 3 over 22. And we now check if this is a correct inverse matrix of the given matrix n. We multiply the given matrix n by n to the minus 1 and we should get an identity matrix. The given matrix n has these entries 3, negative 2, 5, and 4. And we multiply matrix n by n to the power minus 1. We have 2 over 11, 1 over 11. Second row, negative 5 over 22, 3 over 22. And we perform the indicated operation, which is matrix multiplication. We start by multiplying the first row of matrix n. We multiply these entries of the first row by the entries of each column of n to the minus n, and we add the products. And then we multiply the second row of matrix n by the entries of each column of n to the minus 1. And the resulting 2 by 2 matrix should be an identity matrix. To get the entry in the first row and first column of this matrix, you multiply the first row of matrix n by the entries in the first column of matrix n to the minus 1. 3 multiplied by 2 over 11, that's 6 over 11. Plus negative 2 multiplied by negative 5 over 22 is positive 10 over 22. And for us to get a common denominator of 22, we multiply 6 by 2 over 2. And 6 multiplied by 2 is 12, plus 10 is 22. And the common denominator is 22. But 22 over 22 is 1. So the first entry here in the first row and first column is 1. To get the next entry in the first row of this matrix, entry in the first row and second column, we multiply the entries of the first row of matrix n by the second column of matrix n to the minus 1. And we add the products. 3 multiplied by 1 over 11 is 3 over 11. Plus negative 2 over negative 2 multiplied by 3 over 22 is negative 6 over 22. Or you can reduce that to lowest terms. 2 over 22 in lowest terms is negative 1 over 11 multiplied by 3, negative 3 over 11. And positive 3 over 11 plus negative 3 over 11 is equal to 0. Thus, the entry here in the second column and first row is 0. For the entries of the second row, first column, we now multiply the entries of the second row of matrix n by the entries of the first column of matrix n to the minus 1, and we add the products. 5 multiplied by 2 over 11 is 10 over 11. Plus 4 multiplied by negative 5 over 22. 4 over 22 in lowest terms is 2 over 11. And multiplied by negative 5, we get negative 10 over 11. But the sum of positive 10 over 11 and negative 10 over 11 is equal to 0. Thus, the entry here in the second row and first column is 0. Finally, we get the entry here by multiplying the second row of matrix n by the second column of the matrix n to the minus 1, and we add the products. 5 multiplied by 1 over 11 is 5 over 11. Plus 4 multiplied by 3 over 22. But 4 over 22 can be reduced to lowest terms. 4 over 22 is 2 over 11. Multiply that by 6, that's 12 over 11. Again, 4 multiplied by 3 over 22. 4 over 22 can be reduced to lowest terms, that's 2 over 11. 2 over 11 multiplied by 3 is 6 over 11. And to 6 over 11, we add the product. 5 times 1 over 11 is 5 over 11. 5 over 11 plus 6 over 11 is 11 over 11, or 1. And we have shown that the product of the matrix n, the given matrix n, and the matrix n to the minus 1, which we obtained by using elementary row operations, is an identity matrix of size 2 by 2. Therefore, this matrix n to the minus 1 is the inverse matrix of the given matrix n. Or the inverse of matrix n is this matrix n to the minus 1 with these entries: 2 over 11, 1 over 11, negative 5 over 22, and 3 over 22. We now take another example in which we will have a square matrix of size 3 by 3. For our second example, we find the inverse of the following 3 by 3 matrix. With entries in the first column, negative 2, 3, 0. Entries in the second column, 1, negative 1, 1. And entries in the last column, 0, 2, 5. As what we did in example 1, we write initially the matrix A adjoined with the identity matrix of size 3 by 3, where we have 1 in the diagonal and 0 elsewhere. Initially, we write the matrix of this form AI, where A is the given 3 by 3 matrix, and I is the identity matrix of size 3 by 3. And this is that matrix. The given matrix A and the identity matrix of size 3 by 3. And our objective is to transform this matrix AI into an equivalent matrix of this form I, identity matrix of size 3 by 3, and a matrix denoted by A to the minus 1. And after the transformation, we would check if the matrix we get, A to the minus 1, is the inverse of matrix A by multiplying A by A to the minus 1. And if A to the minus 1 is the inverse of A, we should get a product of I, identity matrix of size 3 by 3. And to transform this matrix into this equivalent matrix, we have to change this into an identity matrix of size 3 by 3. And we start with the first column. For an identity matrix of size 3 by 3, the first entry in the first row and first column should be 1. So we have to change negative 2 to 1. And if we change negative 2 to 1, we have to change all the entries of row 1. To make negative 2 into, to change negative 2 to 2, to change negative 2 to 1, either you divide all the entries of row 1 by negative 2, or multiply the entries of row 1 by negative 1 over 2. Or to change negative 2 to 1, multiply the entries of row 1 by the reciprocal of negative 2, which is negative 1/2. And we perform this operation. This is the second type of elementary operation, where row 1 is replaced with the scalar multiple of row 1, with 1/2 being the scalar. Or we simply divide row 1 by negative 2. Negative 2 divided by negative 2 is 1. 1 divided by negative 2 is negative 1/2. 0 divided by negative 2 is 0. 1 divided by negative 2 is negative 1/2. 0 divided by negative 2 is 0. 0 divided by negative 2 or 0 multiplied by negative 1/2 is 0. And the entries of row 2 and row 3 are the same. We are still working on the first column. Our objective is to make this first column of matrix A into a column with entries 1, 0, 0. And we already have 1 in the first row and first column. Now we make 3. We change 3 to 0. And if we change 3 to 0, we have to change all the entries of row 2, because 3 belongs to row 2. And when changing an entry to 0, we always take its negative. The number to be changed to 0 is positive 3 multiplied by negative, or take its negative, you get negative 3. And we multiply negative 3 by a row where there is 1 in the first column. And we have 1 in row 1 in the first column. So we multiply negative 3 by row 1. And to this negative product, negative 3 times row 1, we add row 2. We perform this operation, multiply the entries of row 1 by negative 3. And this is row 1. Multiply all these entries by negative 3. 1 multiplied by negative 3 is negative 3. Negative 1/2 multiplied by negative 3 is positive 3 over 2. Zero multiplied by negative 3 is 0. Negative 1/2 multiplied by negative 3 is positive 3 over 2. And the last two zeros multiplied by negative 3, you get 0 and 0. And to these entries, we add the odd entries of row 2. They are 3, negative 1, 2. 0, 1, 0. Negative 3 plus 3 is 0. 3 over 2 minus 1. For us to have a common denominator of 2, we multiply negative 1 by 2 over 2. Negative 1 multiplied by 2 over 2 is negative 2 over 2. Negative 2 plus 3 is 1. Common denominator is 2. 1 half. And 0 plus 2 is 2. 3 over 2 plus 0 is 3 over 2. 0 plus 1 is 1. And 0 plus 0 is 0. These are the new entries of the second row. And the entries of the first row are the same. Entries of the third row are the same. Now you can see the entries in the first column are now 1, 0, 0. Our objective is to change these entries of matrix A negative 2, 3, 0 into entries 1, 0, 0 in the first column. And we already have 1, 0, 0. Now we go to the second column. In the second column, we should have 1 in the second row. So we start by changing 1 half to 1. And to change 1 half to 1, we have to, if we are to change 1 half to 1, we have to change all the entries of row 2 by using an elementary operation. And to change 1 half to 1, we simply multiply 1 half by its reciprocal, which is 2. So 2 multiplied by 1 half is 1. But we have to multiply all the entries of row 2, not just 1 half. Again, if we have to change 1 half to 1, we have to change all the entries of row 2. And to change 1 half to 1, we have to multiply 1 half by its reciprocal, which is 2. And 2 we multiply by row 2. Entries of row 1 are the same. 1, negative 1 half, 0, negative 1 half, 0, 0. Now we multiply row 2 by 2. 0 multiplied by 2 is 0. 1 half multiplied by 2 is 1. 2 multiplied by 2 is 4. 3 halves multiplied by 2 is 3. 1 multiplied by 2 is 2. And 0 multiplied by 2 is 0. The entries of the last row are the same because we only operate on the second row. So So we already have 1 in the second row and second column, and the rest of the entries in the second column must be 0. Negative 1/2 should be changed to 0, and 1 here should be changed to 0. We start with negative 1/2. If we are to change negative 1/2 to 0, we have to change all the entries of row 1. And the number to be changed to 0, we take its negative. The number to be changed to 0 is negative 1/2. We take its negative, or we multiply it by negative 1. So 1/2 take its negative is positive 1/2. And we multiply positive 1/2 by the row where in the second row where we have 1. Second row, we should have 1 in the second row and second column. So this must be 1. And it's already 1, and we multiply 1/2 by row 2. And to this product, we add the old entries of row 1. Multiply the second row by 1/2. This is the second row. 0, 1, 4, 3, 2, 0. Multiply these entries by 1/2. 0 multiplied by 1/2 is 0. 1 multiplied by 1/2 is 1/2. 4 multiplied by 1/2 is 2. 3 multiplied by 1/2 is 3/2. 2 multiplied by 1/2 is 1. And 0 multiplied by 1/2 is 0. And to these products, we add the old entries of row 1. We have 1, negative 1/2, 0. Negative 1/2, 0, 0. And we perform the operation addition. 0 plus 1 is 1. 1/2 plus negative 1/2 is 0. And 2 plus 0 is 2. 3/2 plus negative 1/2 is 1. 1 plus 0 is 0. 0 plus 0 is 0. And these are the new entries of row 1. The entries of the second and third rows are the same because we only operate on row 1. We are still operating on the second column. In the second column, we should have 0, 1, 0, and we already have 0, 1. Now, this entry 1 must be changed to 0. And if we change 1 to 0, because 1 belongs to row 3, we have to change all the entries of row 3. The number to be changed to 0 is 1, and we take its negative, or we multiply it by negative 1. Multiplied by 1 is negative 1. And we multiply negative 1 by by the row in the second column where we should have 1. And we should have 1 in the second row, second column. Hence, we multiply negative 1 by R2. And to this product, negative 1 multiplied by R2, we add the old entries of row 3. We perform this operation, multiply row 2 by negative 1. Row 2, entries are 0, 1, 4, 3, 2, 0. Multiply each of these numbers by negative 1. And we should get 0, negative 1, negative 4, negative 3, negative 2, 0. And to these entries, we add the old entries of row 3, which are 0, 1, 5, 0, 0, 1. And we add, we have 0 plus 0 is 0. Negative 1 plus 0 is 0. Negative 4 plus 5 is 1. Negative 3 plus 0 is negative 3. Negative 2 plus 0 is negative 2. And 0 plus 1 is 1. These are the new entries of row 3. The entries of row 1 and row 2 are the same. The new matrix now is this matrix. In the first column, we have 1, 0, 0, 1, 0, 0. In the second column, we now have 0, 1, 0, 0, 1, 0. In the third column, we should have 0, 0, 1. But in the third column, we have 2, 4, 1. And the entry in the last row, third row, and third column is already 1. So we only have to change 2 to 0 to make it 0. And we also have to change 4 to make it 0. So we perform 2 elementary operations to change 4 to 0 and to change 2 to 0. We now change the number, this entry 2 to 0. And if we have to change this to 0, we have to change all the entries of row 1. So we perform an operation on row 1. And the number to be changed to 0, we should take its negative, or we should multiply it by negative 1. The number to be changed to 0 is 2. We multiply it by negative 1, or we take its negative, and it becomes negative 2. And we multiply negative 2 by the row where we should have 1 in the first column, and we should have 1 in row 3 in the third column. Again, we multiply negative 2 by the row where we should have 1 in the third column. And we should have 1 in the third row, third column. Hence, we multiply negative 2 by row 3. And to this product, we add the entries of row 1. We perform this operation, we multiply the entries of row 3 by negative 2. These are the entries of row 3, 0, 0, 1, negative 3, negative 2, 1. We multiply them by negative 2. We should get 0, 0, negative 2, positive 6, positive 4, and negative 2. 0, 0, negative 2. 6, positive 4, negative 2. And to these products, we add the old entries of row 1. 1, 0, 2, 1, 1, 0. And we add the operation involved with addition. We add 0 plus 1 is 1. 0 plus 0 is 0. Negative 2 plus 2 is 0. 6 plus 1 is 7. 4 plus 1 is 5, and negative 2 plus 0 is negative 2. And these are the entries, the new entries of row 1. We also have to change 4 to 0, and 4 belongs to the second row, so we change all the entries of row 2. And we perform an operation on row 2. In row 2, the number to be changed to 0 is 4, and we take its negative, or we multiply positive 4 by negative 1, and we get negative 4. Again, we multiply negative 4 by the row where we should have 1 in the third column. And we should have 1 in the third row and third column. We multiply negative 4 by row 3. And these products we add to the old entries of row 2. We perform the operation multiply row 3 by negative 4. These are the entries of row 3, 0, 0, 1, negative 3, negative 2, positive 1. Multiply each of these entries by negative 4. We get 0, 0, negative 4. Negative 3 by negative 4 is positive 12. Negative 2 by negative 4 is positive 8. And 1 multiplied by negative 4 is negative 4. And to these products, we add the old entries of row 2. We have 0, 1, 4. 3, 2, 0. We perform the operation addition. 0 plus 0 is 0. 0 plus 1 is 1. Negative 4 plus 4 is 0. Twelve plus 3 is 15. 8 plus 2 is 10. And the last entry, negative 4 plus 0 is negative 4. And these are the new entries of row 2. And the entries of row 3 are the same. We now write the equivalent matrix, the matrix equivalent to this matrix. The new entries of row 1 are 1, 0, 0, 7, 5, negative 2. And the new entries of the second row are 0, 1, 0, 15, 10, negative 4. And the entries of the last row are the same, 0, 0, 1, negative 3, negative 2, 1. Now we have obtained the equivalent matrix I. This is the equivalent matrix of the form I and A to the minus 1, where I is the identity matrix of size 3 by 3. This is the identity matrix I of size 3 by 3. And this other matrix is the matrix A to the minus 1. Now we check if this is the correct inverse matrix of the given matrix A by multiplying matrix A by A to the minus 1. The original matrix A has entries negative 2, 3, 0. Entries of the second column, 1, negative 1, positive 1. Entries of the last column, 0, 2, 5, multiply matrix A by the matrix A to the negative 1, 7, 15, negative 3. 5, 10, negative 2. And negative 2, negative 4, 1. We start with the entry in the first row and first column, obtained by multiplying the entries of the first row by the entries of the first column of the matrix A to the minus 1. Negative 2 multiplied by 7 is negative 14, plus 1 multiplied by 15 is 15. So we have negative 14 plus 15 is 1. And 0 multiplied by negative 3 is 0. And 1 plus 0 is 1. The entry in the second row, the entry in the first row and second column is obtained by multiplying the first row by the second column. We have negative 2 multiplied by 5 is negative 10. 1 plus 1 multiplied by 10 is 10. So we have negative 10 plus 10 is 0, and 0 multiplied by negative 2 is 0. And 0 plus 0 is 0. The entry in the first row, third column is obtained by multiplying the first row of the first matrix by the third column of the second matrix. We have negative 2 by negative 2 is positive 4. 1 multiplied by negative 4 is negative 4. And positive 4 minus 4 is 0. And 0 multiplied by 1 is 0. And 0 plus 0 is 0. We are now in the second row. We start with the first column, second row, first column. Multiply the second row of the first matrix by the first column of the second matrix. 3 by 7 is positive 21 plus negative 2 multiplied by positive 15 is negative 15. So that's 21 minus 15 is positive 6. Plus 2 multiplied by negative 3 is negative 6. So that 6 minus 6 is 0. The entry here in the second row, second column, multiply the second row by the second column. We have 3 multiplied by 5 is positive 15. Plus negative 1 multiplied by 10 is minus 10. 15 minus 10 is 5. And plus 2 multiplied by negative 2 is 4. 5 minus 4 is 1. The entry here in the second row, third column is obtained by multiplying the second row by the third column. Positive 3 multiplied by negative 2 is negative 6. Plus negative 1 multiplied by negative 4 is positive 4. That's negative 6 plus 4 is negative 2. And 2 multiplied by positive 1 is 2. We have negative 2 plus 2 is 0. Now the entries of the last row, we start with the third row, first column. We multiply the first row of the first matrix. We multiply the third row of the first matrix by the first column of the second matrix. 3 multiplied by 7, 0 multiplied by 7 is 0. Plus 1 multiplied by 15 is positive 15, 0 plus 15 is 15. Plus 5 multiplied by minus 3 is minus 15. We have 15 minus 15 is 0. Entry here in the second row, second column is obtained by multiplying the third row by the second column of the second matrix. 0 multiplied by 5 is 0 plus 1 multiplied by 10 is 10. 0 plus 10 is 10. Plus 5 multiplied by minus 2 is negative 10. We have 10 minus 10 is 0. And the last entry here is obtained by multiplying the third row by the third column. 0 multiplied by negative 2 is 0 plus 1 multiplied by minus 4 is negative 4. 0 minus 4 is minus 4. And plus 5 multiplied by 1 is 5. We have minus 4 plus 5 is 1. So we have shown that the product of the given matrix A and the matrix A to the minus 1 is the identity matrix of size 3 by 3. Therefore, this matrix A to the minus 1 with this entry 7, 5, negative 2, 15, 10, negative 4, negative 3, negative 2, 1 is the inverse matrix or the inverse of matrix A. And this inverse matrix of A is correct because when we multiply A by A to the minus 1, the product is an identity matrix of size 3 by 3. For your practice, please try the following exercises. In the following exercises, find the inverse of each and check your answer. That is, multiply the given matrix by the inverse that you get, and see if the product is an identity matrix. For number 1, find the inverse of matrix E. It's a 2 by 2 matrix with entries 3, 1/3, 2, -1. Number 2, find the inverse of matrix F. It's a 3 by 3 matrix. Entries in the first row 1, -3, +2. Entries in the second row 0, 2, -4. Entries in the third and last row -1, 0, 7. And that ends our lesson for today on inverse matrix. Finding the inverse of a matrix using elementary row operations. If you have questions about the lesson today, please ask your questions in the comments below. And thank you for joining me in my class today in linear algebra.